Okay, so here's graphing. We want to find the domain, range, and asymptotes of each. So in our last lesson, we talked about exponential functions, and that's what we have right here. F of x equals 4 to the x. That's an exponential function. And here, notice the notation, f inverse of x is equal to log base 4 of x. That's because logarithmic functions and exponential functions are inverses of one another. So let's graph the first one, f of x equals 4 to the x. And I'm going to do this in a color so that you can see. We know that the domain of an exponential function is negative infinity to positive infinity. Our range of this standard function is going to be 0 to infinity. It's going to have an intercept. If you got your practice in, it's going to have an intercept at 0, 1. When you put a 0 in for x, you get a 1 out. But you can never get a 0 for y. So you'll never have an output of 0. So you have an asymptote at the equation y equals 0, which is your x-axis, and it's horizontal. Our inverse function is going to take all the points of our exponential function, negative 1 1/4, negative 2 1/16, 0 1, 1 2 3 4, 2 16. I'm going to put that way up here. We'll put that right up there. That's 2 16, 2 2 2 16. Here we have 1 4. Here we have 0 1. And then we have negative 1 1/4. That's that next point. And since I can't write the next ordered pair, I'm just going to take that one out. We'll just delete that one. Delete there. But I'm going to draw it. So here we've got, there we go. So we've got this beautiful exponential function, right? And it has a horizontal asymptote at y equals 0. So I'm color coding. I picked yellow on purpose because yellow goes with the exponential function. Now our logarithmic function is going to take all these ordered pairs and it's going to flip them. So instead of negative 1 1/4, we're going to have 1/4 negative 1. And instead of 0 1, we're going to have 1 0. And instead of 1 4, we'll have 3 4 1. 1 2 3 4 1. And then instead of 2 16, we're going to have 16 2, which is going to be way out there. So you can see what happens. And instead of a horizontal asymptote, we are going to have a vertical asymptote. And I'm going to highlight that in green because it does go with the logarithmic function. So our domain, remember our domain, x has to be greater than 0. So our domain is 0 to infinity. Isn't it interesting how the range and the domain are flip-flopped? That's because that's what happens in inverse functions. We already know this. Our range, our outputs, are going to go from negative infinity, and then even though this doesn't seem like it's increasing, I'm going to go out further, and then I'm going to go up a little bit, and out further, and up a little bit, and out further, and up a little bit. So I'm always going to be going up very slowly, but I will be able to achieve going up towards positive infinity. And then our intercept here, if you look at your intercept for your exponential function, it's no surprise that our intercept for this function is 1, 0. So in this case, we have an x-intercept. So this is an x-intercept. Over here, in our exponential function, we have a y-intercept. And then our asymptote is not y equals 0, it is x equals 0. It is a vertical asymptote. So logarithmic functions have vertical asymptotes. Exponential functions have horizontal asymptotes. And these graphs, because they're inverses, are going to be symmetrical. I don't know if you remember this. They will be symmetrical about the line y equals x. So they got a really cool thing happening here. That's our line y equals x. So I'm going to just draw that. And you can see the beautiful symmetry that exists. And that will happen with all inverse functions. They will be symmetrical about y equals x. Let's write that. All inverse functions. All inverse functions and their original function, right? Are symmetrical. I could have just said all inverse functions, but I wanted you to kind of make that connection that you've got an inverse function and an original function. All inverse functions are symmetrical about the line y equals x. Okay, let's try another one. F of x equals log base 2 of x, and f inverse of x is equal to 2 to the x. So now our original function is our log function, and our inverse function is 2 to the x. So I'm going to show you how you are going to graph this. There's a couple of different ways you can do this. I'm going to make an x, y chart. Now y is the same thing as log base 2 of x. And I'm going to put f of x here. F of x. That's just another way to say y. But this time it's easier if we kind of think of this in terms as y equals log base 2 of x and say 2 to what power? So we're going to have 2, let's say 2 to the negative 2 power. So you put a negative 2 in for y. 2 to the negative 2 power is 1/4. If I put a negative 1 in for y, 2 to the negative 1 power is 1/2. If I put a 0 in for y, 2 to the 0 power is 1. If I put a 1 in for y, 2 to the first power, 2 to the 1, 2 to the first power is 2. And if I put a 2 in, 2 to the second power is 4. And if I put a 3 in, 2 to the third power is 8. So you end up getting your perfect square, your result of your base raised to your exponent. That's going to be your argument. So remember, that's your result. After you take your base and raise it to an exponent, your result is your argument, and your x values are your result. So these x values are your result. Now remember, your argument has to be greater than 0. It has to be positive. And look at what happened there. All of your inputs were greater than 0. So when I put a 1/4 in, we get negative 2 out. When we put 1/2 in, we get negative 1 out. When we put 1 in, we get 0 out. When we put a 2 in, we get a 1 out. When we put a 4 in, 1, 2, 3, 4, we get a 2 out. And then the next number that we can put in is an 8, we get a 3 out. Now this isn't the easiest way to graph a log function. I'm going to be honest with you. This is not the easiest way. I'm going to say we've got our vertical asymptote at x equals 0. So there's your vertical asymptote at x equals 0. We've got a domain of 0 to infinity, a range of negative infinity to positive infinity, an intercept at 1, 0, a vertical asymptote at x equals 0. Now, what I normally do is I normally graph the exponential first. The exponential function is much easier to graph. Rather than going backwards and putting values in for y and getting values out for x, it's much easier to just put some values in for x. You put a negative 2 in and you get 1/4 out. You put negative 1 in, you get 1/2 out. You put a 0 in, you get 1 out. You put a 1 in, you get a 2. 2, you get a 4. 3, you get an 8. And then what I do with each one of those points is I flip them. So you put a 3 in, you get an 8, and that's how I get 8, 3. You put a 2 in, you get a 4, and that's how I got 4, 2. You put a 1 in, you get a 2 out, and that's how I got 2, 1. Here you put a 0 in, you get a 1 out, and that's how we get 1, 0. Same thing with our fractions. You put a -1 in, you get 1/2 out, and here you put 1/2 in and you get -1 out. So I usually graph the exponential function, and then I reverse the inputs and outputs to get my log function. And the color coding most definitely helps. Our domain for our log function is in blue. Our range, intercept, vertical asymptote, that's all in blue. Our domain, range, intercept, asymptote for our exponential function is going to be in red. It's -infinity to +infinity because we can put anything in. We can put all real numbers in for x. Our range is only going to give us 0 to infinity, not including 0. Our intercept is 0, 1. Our asymptote is y equals 0 on an exponential function. You've always got that horizontal asymptote, not your vertical asymptote. So now let's try graphing when we only have one log function to graph. Y equals log base 3 of x. So what I do first is I graph the exponential y equals 3 to the x. Now why did I choose 3? Because the base is 3. So I'm going to graph y equals 3 to the x. I put a -1 in and I get 1/3. Okay, -1, you get 1/3. Let's put an x and a y. I put a 0 in and I get a 1 out. I put a 1 in and I get a 3 out. I put a 2 in and 3 squared is 9. I get a 9 out. And I'm not going to connect those dots because that's not the graph I want. The graph that I want is this one right here. I want y equals log base 3 of x. So I'm going to reverse the inputs and outputs. Instead of -1, 1/3, I'm going to have 1/3 -1. Instead of 0, 1, I'm going to have 1, 0. Instead of 1, 3, I'm going to have 3, 1. And instead of 2, 9, I'm going to have 9, 2. And then I have a vertical asymptote because my domain is 0 to infinity. So I've got that vertical asymptote at x equals 0. So my domain is 0 to infinity. My range is -infinity to +infinity. The graph goes down forever, that's -infinity, and eventually it will go up forever to +infinity. Our intercept is at 1, 0, and our asymptote is a vertical asymptote at x equals 0. Asymptotes are always equations of vertical lines. Okay, I believe this is our last one. Now, when you have a more complex argument, it's always a good idea to think about your domain first so that you can get an idea, what is my domain going to be? So my domain is going to be x minus 1 is greater than 0, meaning x is greater than 1. That's also going to tell us our asymptote. That means your asymptote is going to be at x equals 1. Okay, so I'm gonna graph that first. My asymptote is at x equals 1. And all my inputs are going to be to the right. Now I'm going to go back to what I did in number 15. And I'm going to say, let's graph y equals, it's a base 3, so let's graph y equals 3 to the x. And then I'm going to shift right 1. So everything's going to get shifted right 1, as evidenced by our asymptote that's normally on the y-axis. It's shifted right 1 at x equals 1. So I'm going to plot these in gray. Negative 1 1/3, 0 1, 1 3, and then 2 9. And I'm probably going to go back and I'm going to erase them because I don't want them to be part of my graph. They're just there as a guide. And now I'm going to reverse the inputs and outputs and then shift right 1. Because this is going right 1, all of my x values are going to add 1. So I'll show you what I mean. So let's start with this easy one right here, 2 9. So 2 9 becomes 9 2, but then we're going to go right 1. So when we go right 1, we get 10 2. Okay, let's try again. So we're going to take our ordered pair of 1, 3, and it's going to become 1 2 3, 1. But then we're going to go right 1, so 3, 1 becomes 4, 1. So right 1 equals 4, 1. And then we had 0 1 is going to become 1 0, but 1 0 right 1 becomes 2 0. That is part of my arrow. That was part of my arrow. Oh, see, I just make these arrows that look like dots. There we go. So right 1 becomes 4 1. 1 0, right 1 becomes 2 0. And there's our graph. Now perhaps I did a little bit too much in one step. So let me, for those of you who need a little bit more than that, let me do this in blue and then I'll move to red. Okay, so first we're going to take our ordered pair, 2 9, and it will become 9 2. Okay, 9 2. And then 1 3 becomes 1 2 3 1. So there's 3 1. And then our ordered pair 0 1 becomes 1 0. And then the next one is negative 1 1/3, so 1/3 negative 1. We're going to take each one of these points and we're going to move it right 1. So right 1, right 1, right 1, right 1. Then I'm going to connect the red points. And that's our answer. Everything got shifted right 1. So hopefully one of those two ways made sense to you. Right 1 means add 1 to your x value. That's what I tried to demonstrate in the last video. But if that doesn't make sense, do it just in little pieces. Graph y equals 3 to the x. Then flip your x's and y's. Right? So flip your ordered pairs to graph y equals log base 3 of x. And then step 3, translate your points according to the problem, and in this case it was translate all those points right 1. And then we can write our domain as 1 to infinity, which makes sense. We already knew that right here. Our range is always negative infinity to positive infinity on a logarithmic function. Our intercept here is 2, 0. And our asymptote is a vertical asymptote, but at y equals 1. So this video might be worth maybe watching a second time, getting a really strong handle on graphing logarithmic functions. It's not the easiest, but with practice, it's not the hardest thing either. So give yourself that opportunity to get that practice in your worksheet. And when you check your answers, I've provided some solid solutions, worked out solutions that hopefully will be able to guide you if you get